Hello and welcome to the Weekly Space Hangout for Wednesday, April 4th, 2018. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about, finally, the Tiangong satellite return to Earth. Finding false Earths, NASA's working on a new supersonic plane, and a bunch of wacky transient events detected in various galaxies. Joining me this week, as always, our regular cast crew, we've got Dr. Paul Matt Sutter.
Here I am, apparently in the slow zone.
In the slow zone. You're lagging. There's like some kind of relativistic effect that's going on. So maybe Einstein didn't cover this.
I don't remember that part of the general relativity equations, field equations.
Of course, Dr. Sutter is an astrophysicist at Ohio State and the host of Ask a Spaceman. We've also got Dr. Kimberly Cartier, the Earth and Space Science reporter for EOS Magazine. Kimberly.
Hey, Fraser. Happy podcast day, everyone.
Happy podcast day to you, too.
It's honestly my favorite day of the week.
Wait, is podcast day every Wednesday? Who decided that?
Podcast day is whatever day you listen to this podcast.
Or whatever day we record it.
No,
well, for me, I don't like listening to myself, so I don't always listen to the podcast, but whenever I do, it's always Wednesday morning, so I can say that I did it by the time we get here.
You were dutifully listening to the podcast for a little while there and giving us really great feedback. In fact, I would say
most of the feedback seemed to focus on me. I'm just like you weren't very self-critical.
What can I say? What can I say, Paul? You talk a lot.
Oh. And joining us as a special guest, returning guest, and also sort of a part panelist for today is Mathew Anderson from Our Cosmic Story. Mathew, welcome back.
Thank you, Fraser. Really happy to be here. It was a great time last time, and the topics you just mentioned are going to be really good for this show, so I'm glad to participate.
All right, so before we get into talking with Mathew about his new project and the other stuff we're going to do, just want to remind everyone a big thanks to the Weekly Space Hangout crew. This is, of course, the community. They provide the chat that's down at the bottom. If you want to be a part of this, go to wshcrew.space, and they'll give you instructions if you want to join the Slack community, and we're having a good time, so come and join us. All right, let's get on with, first, the special guest. Mathew, for people who perhaps don't recall where you come from and what you do, who are you? What do you do?
Well, I'm a Texan now, and I grew up in Wisconsin, and we had a lot of astronomy parties there. I remember in high school, just the very beginning of my career, I was always fascinated with space, and my career took a little bit of a course change. I actually am primarily a community manager in the computer game industry, and have kept the astronomy part of it as a strong hobby. And just the last few years, when I was on the show last time, I was talking about my other book, Our Cosmic Story, and have continued that tradition of writing books in the time I have.
And so just now, your new book, I'm going to bring it up beside you here. Hold on. Let's see if I can do this here. There we go. Mathew Anderson, Habitable Exoplanets, Red Dwarf Systems Like TRAPPIST-1. Can you hold it up? Let's see the real book.
Yeah, so it's right here. Here, I'll cover my face here. I think we got to. There we go.
Side by side now.
So it's going to be primarily in ebook on Amazon. All my books right now are available at amazon.com/author/Mathew Anderson. That's one T in Matthew. I sound like a promotional advertisement right now, but there it is.
Yeah. So what's the new book about?
So as a real quick recap, Our Cosmic Story gave a big picture view of life on Earth, how it came about, and the chances for life and civilization elsewhere in the universe. And as I was writing that book, one chapter later in the book really grabbed me about, well, this topic is heating up in astronomy and it really needs more. And I surprisingly have not found a lot of books about exoplanets yet on Amazon or elsewhere. And I thought, well, let's write one, but let's write one about exoplanets with a twist.
And the twist is red dwarf stars?
Exactly. So red dwarf stars, you have to read the book for the details, but basically they're like at least 70% of stars in the universe that we know of, and they demand our attention because we've been starting to find more and more exoplanets around them, and some very intriguing ones too.
So why don't you tell me about some of the coolest red dwarf stars and some of the exoplanets that have been found?
Well, there's the book I pretty much focus. There's so many that we're finding now around these stars, and we're going to find more hopefully in a couple of weeks with Tess that's launching. Well, it'll take a while for it to see first light and everything, but the one I focus on is TRAPPIST-1, which I know our panelists here know all about, and probably a lot of you in the chat that I'm watching here right now probably would give a nod. Yes, I've heard of TRAPPIST-1, so I pretty much focus on that system.
And so what sort of makes the TRAPPIST, for people who maybe don't know, what makes the TRAPPIST-1 so interesting and a fascinating target?
Well, it's amazing. We found 7 planets in the system, which almost rivals our own solar system. So it's the count of the planets, but it's also this compact structure or mechanics that the system has. They are so close to each other. These planets, which are all similar in size to Earth, they're not, except for a couple super Earth technical category, but there's a few that are a little smaller, but relatively Earth-sized, and 7 of them in one system, all orbiting within what we would consider the orbit of Mercury in our own solar system. So this is like a mini solar system, and you might think, well, things can be smaller, right? Why not? But the weird thing is that planets like that aren't very stable that close together, and the only way TRAPPIST-1 and who knows how many other red dwarf systems are out there like this can remain that close together, their planets, is a special resonance that they've developed.
So what would it be like, though, to have some kind of habitable world around one of these places? What's the downside?
Oh, wow. So this is where the book really gets into the potential positives and the potential downsides. And the thing is that we're not really sure yet if these planets are even habitable at all. There's a lot of things, starting with the parent star and the active flaring of that star. These small stars, small compared to our sun, are extremely active. They throw out flares that are hundreds, if not 1,000 times more powerful than our sun can produce, and that would put a really bad sunburn on you if you were exposed to that.
Actually, just saw today, one of these flare stars would wipe out the ozone layer, would kill 94% of the ozone layer within 2 years.
It's
but
just, there's a
and that's just 2 years of exposure to being this close and to these kinds of powerful flares.
Yeah, the interesting thing about these flares, though, and in the book I talk about the flares first and the parent star, because that's what gives for our sun life, and that really what matters for a habitable planet. If the star is acting up too much, the planet may not be able to protect against that. But the interesting thing is that these red dwarfs have different type of flares. They're more powerful, and they're more frequent, especially in the early years of the star, where the first 500 million years or so is really active. Then they settle down a little bit. But the flare types are different too. They don't emit as much protons, and that is something that we're really that scientists, I should say, are taking a real close look at, is these different types of flares may not actually be as detrimental to an atmosphere.
Really?
Yeah, there's I should say first to the magnetic field, if there is one around a planet, which is what I get into in the book next. So you've got a few components here really to consider around red dwarfs, but really around any star system. The star itself, how active is it? The planet, how shielded is it with any sort of magnetic field, like an intrinsic one like we have, or an externally induced one, which is an interaction with the star's solar wind, and the planet's atmosphere itself can set up an ionization field to protect the atmosphere. And then you have the atmosphere that protects the water, and of course we like water as life.
Right. Yeah. And I mean, that's one of the other problems. That's one of the problems with Mars is that it, you know, just the solar wind blasting off the sun would tear away the Martian atmosphere, has torn it away in the past. And even if we got a chance to build a new atmosphere around Mars, it would just get working to tear it apart all over again.
Yeah, but here's another cool thing. Mars, we really think that Mars is just simply too small. It's unfortunately didn't get enough mass. It's not big enough. And that's the primary reason why it lost its atmosphere. If it had a magnetic field at one point, a global magnetic field, an internal dynamo, active inside the planet, all of these things just shut down because the planet cooled off too quickly. That's why we have a really thick atmosphere still around Venus. It doesn't have an internal magnetic field, but the atmosphere is able to still buffer the solar wind enough. And while there's no water on the planet for other reasons, the gravity is able to keep most of that atmosphere there.
So did you get a chance to talk to some researchers while you were doing the book?
Yeah, it's funny. I was, I don't know if you've been to South by Southwest here in Austin, but I met a few researchers here. There was, I'm sorry, I forget his name now, but they had a couple of things that they were doing at that show, at the game booths. South by Southwest does a bunch of things. And I was fortunate enough to meet a couple of guys recently from SpaceX as well, and had a chat with them about the book. And I've been doing interviews the last year since the book's development on a very regular basis, just to try to get as much perspective as I can, or as I could now that the book's finished, on what do all these research papers really mean? Because we have, as you guys know, one research paper come out that would cast doubt on, is there atmospheres around these planets? And then a few weeks later, it'd be like, oh, there could be an atmosphere.
Yeah, I think the most
trying to put that together.
Research is that the TRAPPIST worlds might have too much water now. Have you heard about that? Like, they could be 50% water.
Right. Yeah, that's why one of the main reasons we think that's the case is because the densities of those planets are mysteriously low. And that's one answer to that, is that they are packed with water. And that means a few things. That means, well, they probably have an atmosphere, unless they're all ice capped. And that's not likely I said there were 7 planets. So how we label these planets is we've got the star, and then we've got B, C, D, and everything starts with B for the designations of the planets after that. So TRAPPIST-1, B, C, D, and so on. Those are B and C and D especially are pretty hot, so it's not likely they're ice capped. But once you get to like G and H, then we think, well, maybe they're ice capped and they're just packed with a lot of ice. But some of them are still low density planets, and they are too close to the star really to be ice capped. So they got to have water. And if they have water, they have to have an atmosphere to protect that water.
Right, because they would be having that torn away. Now, what about the tidal locking problem?
Ooh, now this is where it gets special. Tidal locking I want to write another book just about this, because one of the things I try to do in my books, just for everybody watching, so they understand where I'm coming from, because I don't have a doctorate, is, I interview a lot of scientists. I interview a lot of people in the industry. I also have friends in the computer game industry that have a lot of this knowledge and experience. Fraser and I were talking about Richard Garriott a little while ago. And it's one of the things that's most special about these red dwarf planets is that because they're so close to their star, they are like our moon is to our planet. They're locked. They don't rotate with respect to the other body.
But I mean, if we only faced the sun, one side of the Earth faced the sun, that would be suboptimal compared to what we have right now with a day-night cycle, right?
You wouldn't want to be at the focal point of that. You would want to be at what's called the terminator, probably, where it starts to get a little darker, a little light, and all these planets that are almost all these planets that are around red dwarf stars are probably tidally locked because they're so close. They're all going to have that really hot side. They're going to all have that really cold side and that terminator. But there's some exceptions there now. So if the planet has an atmosphere that's as thin as ours with as low carbon dioxide level as ours and other greenhouse gases, and various other factors too. This is very complex, and I take the big picture view, so there's details here I don't even understand myself. But in general, you need a thick atmosphere, you need those greenhouse gases, and at the planet with the right distance, and it could spread out that heat around the globe, which would not only cool the hot side to a degree, but also prevent all the water from locking up on the far side by getting too cold. And that, we think, is what happened with Venus.
Right. And then you mentioned this sort of right at the beginning of the show, that the Tess satellite is going to be taking off in just a couple of weeks now.
Yeah, I think April 16th, if I have that right.
Mm-hmm. So why don't you give people just a quick sort of sneak preview of what the Tess is going to do?
Kimberly or Paul probably could talk a little bit more detail about this, but the Tess is the successor to the
Kepler, the Kepler mission.
Kepler, thank you. Yeah, the Kepler mission, and it's designed to take a good look at a wider view of the sky at once for these transiting planets. So you've got the sun, say take my head as the sun here, for example, and the primary technique that we use that's been most successful is the transit method, which as the planet comes around, here comes my finger.
Remember, for the podcast listeners,
is this good?
He's putting he's putting his finger in front of his face, so he's transiting across his face.
My finger is transiting, and as that happens, the atmosphere of the planet and the size of the mass, or it blocks out a certain amount of light basically, and we can tell how much light and the type of light and all of that.
It's going to be I think, Kimberly, you were mentioning, right, that Tess is just going to sort of comprehensively map out these worlds nearby the sun, right?
Right. So Tess is going to be looking at a few million stars, the few million closest and brightest stars all over the sky. So it's unlike Kepler, which stared at a very small patch continuously for 4 years, Tess is going to be mapping the entire sky in much shorter segments, but it's going to get, I think, something like 85% sky coverage, and looking at millions of planets millions of stars for transits.
What's interesting about that, you're mentioning, Kimberly, millions of stars, and we have to do that. We have to have that wide scope, in part because it's about 1% of stars from our viewpoint transit. So we need to look at a lot of them.
Yeah, so it's not just a matter of which stars have the planets, but which of those planets are in the right orientation for them to actually transit the stars from our point of view. So that's dependent on how far away the planets are from their stars, how big they are relative to their stars. And given that Tess will only look at some patches of the sky for about 27 days at a time, it also depends sort of on the timing of everything as well. So we might still miss a lot, but
well, that's the nice thing about that timing. You mentioned a few days. Well, that's not enough to 27 days, I think you said, is not enough to detect an orbit like Earth from a distant, a star and our distance from it. But red dwarfs, a lot of these red dwarfs,
And especially we know that there are plenty of red dwarf stars within a few dozen parsecs of the sun. So there are certainly hundreds or thousands of those really small, low mass stars, which likely have lots of planets that Tess will be able to detect.
Yeah. Well, Matthew, congratulations on the book. Now, you've got a special gift for people who are listening to this show right now.
I do. So I have the advanced copy of my book, Habitable Exoplanets. and I'd like to give it to everybody who's listening today. I'm so excited about this book. I really want you to see the big picture that I'm trying to write in it. And so I'd like to give it to all of you. And the way to do that is to email me at, I think this is how we were going to do it, Fraser.
Yeah, I think so. So email you at ourcosmicstory@gmail.com and mention the Weekly Space Hangout, and you will send people a free copy, an advanced copy of the book for the next week or so. So, if you're watching this live or if you're downloading the podcast after the fact, then, within about the next week from when we're doing this, I don't know, let's cut this off on a certain day. It's the 4th now, so I don't know, the 11th. Is that right? Ish?
11th sounds good.
Yeah, sounds good. So
hopefully that gives your readers enough time.
And before the book actually comes out, so they'll have a chance to get a sneak peek.
Yeah, I'm already getting emails, it looks like, too.
There you go. Well, they're watching right now. This is live. So, awesome work, Matthew. I look forward to reading it, and it's great to see people researching and writing a popular science book about what is very cutting edge discoveries and research. I mean, it's great to sort of see that stuff get out there and get into the hands of the public.
Yeah, that was actually something else real quick for everybody watching is I am someone who's taken all of this research and trying to put it into a big picture. You can do that too. You can interview people. There's so many tools online to go into data that astronomers collect. In fact, they request that they need the help to search for some of these things, to detect planets. You can find planets we haven't found yet, and that's what's so exciting about this.
Yeah, totally. Now you're going to stick around, and we're actually going to talk about a couple of stories that are in this same field. So we'll get one more story. So by all means, jump in if you have something to contribute. But before we move on, just another reminder, if people want to find out more about your book, where should they go? About all your books, all the stuff you're working on?
You can go to amazon.com/author/Matthew with one T, Mathew Anderson.
Or your website, MathewAnderson.com.
Yeah.
Yeah. All right, let us move on. And I guess the big story, of course, we've been talking about this for weeks. It finally happened. Tiangong-1 crashed back home.
Yep, at long last, China's first space station, Tiangong-1, crashed into the southern Pacific Ocean early Monday morning Universal Time, or late Sunday night over here in the U.S.
It was perfect. It was afternoon,
It was great. It despite being a completely uncontrolled reentry, because China obviously lost contact with the space station back in 2016 and could not control the reentry like they had planned. Still, they were able to estimate the trajectory of the space station and getting more and more accurate as it got closer, and predicted that it would probably go in the ocean. No surprise, because our planet has a lot of ocean. But still, the space station re-entered the atmosphere, broke apart just as planned, so there was no large debris, and all that debris fell into the southern Pacific Ocean, pretty much as far from any civilization as you could get.
Yeah, it nearly made it right into the spacecraft cemetery, right?
Right into where everyone tries to
crash the
spacecraft and satellite, because it's so far away from everything and pretty safe.
So there's quite a bit of hand-wringing about it possibly hitting people, falling on their heads or whatever. Was that even remotely possible?
In a very, 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 very remote chance. Obviously, it could have happened in a very, very small probability, because it was an uncontrolled reentry. Because China could not actually communicate with the space station and hasn't been able to for a few years. So there was always a tiny little itty bitty chance that it could have hit.
I saw a statistic of like 1 in a trillion. Your odds of winning the Powerball are better.
Sure. Yeah. And certainly your odds of getting struck by lightning or eaten by a shark or killed by a vending machine are a lot larger than having been struck by this space station.
But the Chinese had said, sort of up until the end, they had said that they still had control over it, and they said that they were going to ditch it into the spacecraft cemetery.
Well, I can't
there it
speak.
is.
And there it is,
And
ditched
there
into
it
the
is. So I
spacecraft
mean, I can't
cemetery,
speak
right?
to whether they actually had control over it or not. But
And it was
reports
just
say
luck.
that in 2016 they lost the telemetry on it and could not control the reentry as planned. Whether or not that's actually true, because it is a remarkably close crash, I don't actually know how coincidental that is.
Yeah.
But still, I mean, this space station did a lot during its 7 years that it was up in the air. It launched in 2011. It hosted 2 or 3 different crews throughout its lifetime, tested out a bunch of technology for some future Chinese space stations. And actually, I learned it also hosted China's first 2 female astronauts during its lifetime.
Cool.
So it was not only historic in being China's first space station, but it was sort of serving as the launch pad for a bunch of future Chinese missions and sort of the start of Chinese astronauts. So congratulations, and for crashing and not hitting anything important.
Yeah. I mean,
Stick the landing.
It stuck the landing.
landing.
Yeah, exactly.
Yeah, there you go.
And if you wanted to sort of imagine what it was going to look like, all you had to do was just watch Gravity, because in the end, that was the space station that got torn up in Gravity. And of course, every time one of these things happens, I always go onto Twitter and watch for people to put up fake pictures and say that they saw it. And
yeah, but in this case, there's really no chance for fake pictures because it was so far away from any.
Did that stop?
Yeah,
or
but
any
what do you mean?
civilization. I mean, no, of course.
All the
of
person
course
has to
there are
do is
fake
take the
things.
Jules Verne ATV re-entry and just post it to Twitter and enjoy the accolades that come from.
Yeah, I think anyone trying to post a picture that's ostensibly taken from the ground is probably fake. At most, there may be a couple airplanes that might have been nearby that could have snapped something from the distance, but certainly nothing from the ground or with a cityscape in the background or anything like that. That's no. It was in the middle of the Pacific Ocean. I think the closest thing was Tahiti, and that was still many hundreds of miles away. So.
Yeah, I haven't seen any
Perfectly
pictures
safe.
yet.
Yeah, perfectly safe. And there you go. And that's the first one. There's a second space station that's pretty identical that launched 2 years ago. It's 2018 now. So 2 years ago. And it's sort of building on the same technology that Tiangong-1 used. And there's going to be another one, and it's all building up towards a more permanent Chinese space station sort of in the next decade or so.
Yeah. It's amazing to see the amount of Chinese launches that are going off now. I'm seeing them get reported every couple of weeks now. They're sending up various satellites, going through their different launch systems. They're building the Long March 5 that's going to be as powerful as the Saturn 5. Maybe it's the Long March 6. Anyway, by 2030 apparently. So they're going to have a Saturn 5 class super heavy lift rocket built. They're catching up pretty quick.
They are.
Is the Chinese Space Agency doing anything in collaboration with NASA, Roscosmos, with ISRO?
No. Well, they're not allowed, right? So no American agencies are allowed to work with the Chinese. Like, there's literally rules stopping them from being able to do this. Now they could work with other people, and they're expanding into other parts of the globe, but no, there's no sort of collaborations on the horizon with the Chinese whatsoever, which is too bad, right? Like, I think that it would be nice, and one of the great things about the International Space Station was to see all of the different groups working together to build that station. And maybe it was out of necessity, right? It was so complicated that you needed to have all these people to help cover the costs. Who's going to build the robotic arm?
Who's going to build the Canadarm?
Exactly.
I don't know.
Had to be Canada.
I don't know. We're just looking at you, Canada.
I know.
But we're not
I know.
seeing it.
Well, if you name it the Canadarm, what are we supposed to do? We're there. We'll build it. All right. Put an arm on all the things.
It worked.
I'm definitely up for collaboration. We need that because these are expensive, complicated projects. A little bit of competition really helps move us along. I mean, we've seen that time and time again in history. It's almost blown us up a few times, but
yeah, And so, I mean, you're seeing, I mean, the Chinese as well, they're going to be putting in another, they're going to be sending another lander to the moon later this year. They're sending a mission that's going to be going out beyond the moon. And they have said that they're absolutely going to be sending humans to the moon as quickly as they can. So, so that's where it's all headed now. I should really do a deep dive into this because it's quite surprising how far along their human spaceflight program is going. Like, I feel like it's been 13 years, 12 years since they launched their first astronaut. You know?
Yeah, I have to say that I, like you said, I don't know as much about this as I probably could or probably should, just because it's so isolated and non-collaborative. But then there are reasons for that and all that, and I wish that we could be more collaborative in the future. But it's a whole nother ball game over there that you have to learn about. And so I mean, I'm slowly learning about all of this. I had to do a lot of research to be like, oh, when did they launch their first space station? That was really recent, and they're doing so many more. There's already another one up. There's another one planned for a year or two from now. They're going to do a permanent one in less than a decade, and it's sort of the timelines that they're working with are so much shorter than what we're used to here in the US that it's kind of hard to wrap your mind around.
Yeah.
Am I largely unaware of their activities because I'm myopic or because it doesn't get a lot of airplay?
I feel like it doesn't get a lot of airplay over here in the US. I mean, this one only did because it was crashing to the Earth somewhere.
Yeah, I a little from column A, a little from column B.
Okay, fair enough.
Yeah, I mean, I think that, you know, there's some great websites out there that are covering a lot of the launches. Like, I think the best, you know, as the publisher of Universe Today, I've got to say that NASA Spaceflight does a fantastic job of covering launches. They are really crushing it, as well as America Space. So those are two great places, and NASA Spaceflight especially. They cover every Chinese related launch, and you're seeing a ton of launches from them. From the Chinese. And so, and there was an article, and I wish I had it handy. I'll try and dig it up for you guys, just sort of showing the pace of how many launches, and you can just see sort of this acceleration of their launches that they're setting up. They have their own version of the GPS.
That's right.
Yeah, so I mean, you know, they've launched they've got the most powerful radio telescope. They've launched space telescopes. They send humans to space quite a bit now, so it's on. I think, you know, if I was part of the United States and was concerned about space races, that's
the one to pay attention to.
That is the competitor to pay attention to, exactly. Yeah. And I think, you know, some people are having some political talk in the chat, and you know, we don't want to get super political about this, but I think, you know, in no way are we saying that their pace, I mean, this is one of the advantages you get for having a political system that they do, is that they get to just drive this process forward without having to be concerned about being really a representative democracy.
Human rights.
Human rights or any of these things, right? You just, like, if you want to put humans on the moon, you just do it. And so, yeah, we should. I will do I'll do an episode on sort of the state of the Chinese space flight, because I think people would be pretty surprised at how far along it is and where it's going here. And a lot of it is, you know, their human space flight especially is copied Russian technology, stuff they borrowed from the Americans. Like, it's, you know,
I mean, it's pretty spectacular. I would certainly learn a lot if you did such an episode.
I will. I'll get to work. All right, Paul. Speaking of exoplanets.
Yeah, because we were just on that topic. I spotted this really cool paper in the archive, which, for those of you who don't know, every astronomer in the world, when they submit their paper for publication to Astrophysical Journal or monthly notices, the Royal Astronomical Society, or Nature or Science or Physics Review or whatever, also puts their preprint on an archive that's been running since 1991, I think. And it's also contains papers from previous years. So it's basically all of science happening. And every day, astronomers around the world get an email listing that day's papers that were submitted. And it's anywhere between 20 and 70 papers every single day, just in astronomy and astrophysics. So I spotted this paper. It came up in the email, and it had this combination of statistics and pessimism, which is two of my favorite pastimes. And so I couldn't resist. And I added it to our list today, actually, so I could get Kimberly's reaction to it. I'll give the very brief overview of the paper, and then we can talk about it. It's from Claire Marie Guimond and Nicholas Cohen at McGill University, and they're looking ahead at future exoplanet survey missions. So some of the proposals floating around out there, like LUVOIR and HabEx, that are going to be these massive surveys of direct imaging surveys of taking pictures of stellar systems looking for reflected light off of a planet. And there's always this trade-off in astronomy surveys of broad but shallow or narrow but deep. Do we target a few systems and really get tons of high quality data on those systems, but potentially miss out on something because we're looking at the wrong stuff? Or do we try to do a really broad survey and get a little bit of data from a lot of systems? And this paper is asking, if we take that approach where we take a lot of pictures of just get a little bit of data from a lot of systems, because the data aren't going to be so good, are we going to think that some systems are like, oh, there's Earth's twin, there's an Earth-like planet in a right orbit around the right star, turns out to be a false positive? And they find they make some assumptions for the telescopes and everything, and they get this really high number of a 77% false positive rate. And based on this search strategy, we will straight up miss 88% of the actual Earth twins out there. So this is raising some questions about how do we do this smart if we really want to spend tons of money and find another Earth.
Do they have a recommendation on how to do it smart? I mean, it looks like, from what you're saying and from what the paper's saying, it just says, essentially, if we try, we're going to suck and we're going to miss the real ones.
They do outline a couple ideas for reducing the false positive rate. And I think they're pointing out here that there is that trade-off, that if you want to reduce the false positive rate, you have to take deeper dives on each individual target and collect more data. But in the limited lifespan of the mission, that means you're going to be able to sample fewer objects, which means you might miss some genuine Earths out there simply because your survey didn't get to it in time.
Well, would it make sense to do a program like kind of how Tess, we were talking about Tess earlier, a telescope that's going to be launched in a couple weeks, and JWST, James Webb Space Telescope, which is going to be launched in, if it doesn't get delayed again, a little over a year, I think.
Oh, now
but
you've jinxed it.
I'm sorry.
we talked about
2047.
Yeah.
Yeah, but JWST is said to be a good follow-up to what we find with Tess, right?
Yeah, it most definitely is. And I have to say that I've always been very skeptical about the idea of trying to do a direct imaging survey. And I think Paul has outlined a couple of the really big issues in that for direct imaging, you almost have to go into a deep dive with each individual target, because planets, even if they're young and hot and bright, they're shining next to something that is 1,000 times brighter. And in order to tease out the information from a direct imaging signal, you have to take a lot of care and do it right. Otherwise, you're going to miss a lot of information. And while this paper is pessimistic about the chances of finding an Earth twin using a direct imaging survey, I can't say that I was particularly surprised by the numbers. And so the issue that they're highlighting is this issue of what we call the radius albedo degeneracy, where an object of a certain brightness could either be reflecting a lot of light but be very small and reflecting a lot of light per area, or it could be very big and just reflecting a little light per area but just have a lot of area. And when you see this for planets above a certain radius, these planets will no longer be rocky. They'll start to be gaseous like Neptune, or could even be as big as Jupiter, just depending on how much light they're reflecting. But even worse is that the issue with direct imaging surveys is that the systems themselves have to be pretty much face on to us in order for us to see that reflected light. Otherwise, we're just not going to. And it's a combination of factors that's very, very difficult to deal with and to manage. And so I wasn't particularly surprised that there might be so many false positives, because there's so many avenues for errors in direct imaging when you just cast a net and see what you find.
But we talked a bit about, the main methods that are used to find planets today, and the transit method and the radial velocity method are the two ways that people go about this. By direct imaging, that gives you a third way. Well, really a fourth way if you include gravitational microlensing.
There's the other half of my brain saying, well, direct imaging can give you the types of planets that transit method and radial velocity method can't give you. For transit method and for radial velocity method, the systems that you're looking at are more edge on. For transits, the planet needs to pass in front of the star, and for radial velocity, the planet needs to move towards you and away from you to get enough of a signal to detect. But for direct imaging, you need the exact opposite type of system, where the planet and the star are face on you, so you see the full circle of the orbit, or the ellipse of the orbit. And that's a whole different population of planets. And not only that, but you'll get the younger planets and the planets that live further away from their stars. These are the types of planets that direct imaging is better at detecting, but transits and radial velocities are worse. So the other half of my brain says that even if there are so many false positives, which we could learn to weed out, we've done that before, and even if we might miss a bunch of them, which I'm sure that we would do anyway, we would still be probing an entire different population of planets than we would get from any other type of survey, with Tess, with Kepler, with any of the radial velocity surveys
that we weren't seeing before, right? We were only seeing,
maybe not 99%, but it'd still be like a good, we'd get 80% of the 50% that we're not seeing.
Right.
Is there any other way to get face-on planet systems?
You could do something like astrometry, which means you would be seeing the actual physical motions of the star going back and forth based on the tugging of a planet, but those would be an entirely different subset of planets than the other three methods. They'd be very, very massive planets, almost comparable to the sizes of their stars.
So sorry, just to sort of stop you for 1 second. So like say the Gaia mission, right, that is doing astrometry, that is charting the position, the motions and the positions of all the stars in the galaxy, you'd have something like that, but where it's just watching a star, and instead of calculating, say, the rate of it moving forward and back, you're actually watching it make tiny little circles in the sky.
Tiny circles because the planet is tugging it in the tiny circles.
Has this been used to detect a planet yet?
A handful at most. It is extremely difficult to do, and again requires staring at a star for a very long time. It's not.
So I have a question for you, Kimberly. For everybody, I think this is something that a lot of the viewers are probably thinking about right now. Given all that we know, all of the techniques for detecting planets, even the theoretical ones that we 20, 30 years from now will probably have a mission or two out there doing, do you feel that we will maybe in our lifetimes one day have enough samplings of all of these different types of systems and direct imaging of atmospheres to get a relatively confident statistic of, the universe contains about this many Earths?
Eventually, yes. I'm going to be confident and optimistic about that and say, yes, eventually we will have those data. Eventually we will have that number of this is the percentage of planets that are Earth-like. and Earth twins in the habitable zone. I am confident that that number exists and we will find it. And I think
42.
I'm amazed actually how many different methods there are for detecting exoplanets. I'm gonna give you the list here. I just found a good list of them. Radial velocity, which we talk about. Transit photometry, which is the transit method.
Kepler and Tess.
Yeah. Reflection emission modulations.
Yeah.
Relativistic beaming. Ellipsoidal variations. Pulsar timing, which we've done. Variable star timing.
The OG.
Transit timing.
The OG.
Yeah, the pulsar timing was the OG. Yeah. Transit timing. Transit duration variation. Eclipsing binary minima timing. Gravitational microlensing. Direct imaging. And polarimetry. And astrometry.
Yeah.
13.
Yeah, 13 different methods to find that. If we can't find Earth 2.0 with those 13 methods, then
I'm pretty sure if there's a way for astronomers to look at the sky, there's an exoplanet scientist trying to figure out how to use that to find a planet.
Yeah.
Eventually, you'll see the dark matter.
Cosmic microwave background.
Background,
Direct dark matter
AGNs,
detection.
Yeah.
Gamma ray.
Right.
Gravitational wave.
Gravitational waves. Are you kidding? That's it. That's the easy one right there.
Galaxy rotation curves.
Yeah. You detect
all the ways to detect
planet going around a
Russell
star.
diagrams.
It's in there somewhere.
So, if there's a will, there's a way.
Yep.
That's awesome.
So,
all right. So there you go.
get there.
This story ended up on a hopeful
It did.
direction.
And I will say,
Okay, I'm okay with that.
I'm putting my hat in the ring of yes, we should still do direct imaging surveys because we'll still find planets that we wouldn't find otherwise, but it'll be really expensive.
But just don't freak out. Don't get too excited if you think you found Earth 2.0.
Exactly.
All right.
There you go.
All right. Well, I'm going to bring up a story here about NASA announced that they're working on a new, quieter supersonic passenger jet. So showing to the apologize to podcast listeners.
Haven't they been working on this for like 50 years?
Well, right. So back in the day, there's been various supersonic jets, and of course, the one that a lot of people are familiar with as a passenger jet is the Concorde. And there was sort of a bunch of downsides to the Concorde. One was the ludicrous price and the tiny little seats. I've actually sat inside a Concorde in France, and it's hilarious how little everything is. It just feels like you're in the cockpit of a fighter jet, even though you're a passenger in an aircraft. But the other problem with it is that it was super loud, and nobody wanted this flying overhead, passing through their area. And of course, the Concorde, what they did was it had this nose. They could sort of bring it down. They could bring it down its speed and be able to, try and in populated areas not be so loud, but still to be able to fly at supersonic speeds and not have a lot of noise is the goal. And so NASA announced yesterday that they're beginning the work with Lockheed Martin Skunk Works to build the next generation supersonic aircraft that should have a much lower sound footprint. And so again, I'm putting up a picture. It kind of looks like a dart, like a lawn dart as an aircraft. And I can't see that being, the kind of thing that people would get on and go, do a continental flight. So,
will this be a passenger jet then?
Well, they are trying to demonstrate, they're trying to understand and demonstrate the technology to see if, can you make a supersonic aircraft that has a much lower sound profile? So this was going to be able to go, I think they're going to try and fly it at Mach 1.6 and attempt to just minimize the sound of the sound boom as it goes by. And I actually talked to somebody about who was They did a demonstration with an F-18 to see that flew past them to sort of at the distance so people get a sense of how loud this thing was going to be. And he said it was super loud. That it was still really loud, and it doesn't really help that, to even go supersonic.
So they're gonna build this thing. Are they gonna use it for anything? Is it gonna be are they gonna transport cargo with it, or is it just gonna be literally?
I think it's a research.
Yeah, well, I mean, one of the things that NASA does is, one of its arms, National Aeronautics Space Administration. So they not only do space, but they do a lot of work in aeronautical research. And the goal is to help, they've got these great aircraft. They've got one that's got like 14 propellers along. They've done these great solar powered airplanes. They've done a lot of, they did a lot of work back with some of the X program. And so this is their latest X plane. And the goal is just essentially, hopefully, to pass this research along to anyone who wants to build a supersonic airplane that fixes that one big problem. The two, one, ludicrously expensive, and two, incredibly loud. And hopefully they can solve this. So
yeah, so it's this weird intersection to deal with that kind of sonic boom. This is a very tough materials problem and geometry problem and turbulence problem. It's at the convergence of a lot of complicated nonlinear physics to try to mitigate and dissipate this shockwave that's produced while you're traveling faster than the speed of sound.
This is great. So Larry Beckham is saying in the chat that it sounds like a car door slamming when it flies at 55,000 feet as it flies past.
Wow.
So
that's loud.
That's actually
not
as loud as it could be.
Right. I guess that's the question. Have you guys ever heard a sonic boom? I've never actually heard one.
I heard one when I grew up in Wisconsin. Maybe we had the Oshkosh Air Museum over there, but I do remember it.
I think I've heard one.
It's like a clap of thunder, right?
Yeah, it's actually quite loud. It's, from what I remember, and this was like probably 25, 30 years ago at this point, before they banned the flyovers, but it's loud enough to get your attention for sure.
Yeah.
So what sort of time frame are they thinking for this new jet?
Well, so they're going to build a half-scale model, and they're planning to do some first flight tests in 2020.
Okay.
Yeah.
That's not too bad.
Yeah. Yeah. So I think it's, I don't know. I mean,
should we give over-unders of whether it'll be before or after James Webb?
Or before or after you get in the BFR, I think is the better question. Right? Will you get in the BFR and do your point-to-point flight, right? Your ballistic trajectory on the BFR and take 30 minutes to go from downtown Columbus to downtown Rome in 30 minutes.
Great pair of cities.
Yeah, would have saved you a lot of time, Paul.
I needed Rome.
That was where Paul was. Well, you working, was it Trieste? Anyway, it's wherever you were in.
Yeah, I worked in Trieste for a couple of years, but which is like Rome, but not.
Same country.
Good description.
I apologize in advance to all the Italians who just are like, they can't believe it. All right.
Apoplectic.
They're apoplectic. There's one other story. I'll give you the quick version of it. In that astronomers have found 72 examples of super weird, quick supernova-like events, but they don't even really know what they are. And one of the ideas is that they're not seeing actually the supernova. They're seeing some kind of like hot gases that are being ejected, and then that's being brightened up. So they've been finding these as part of the Dark Energy Survey program. I'll bring this up here. The DESSN, and they have found these bright explosions as bright as a whole galaxy, and they don't really know what's causing them.
Turns out this is an interesting, I'll just comment on this briefly. This is an interesting direction that astronomy is moving in. You'll see more and more of this over the next few years and decades, is transient astronomy, the astronomy of very, very short time scale bleeps and bloops and explosions. Radio astronomy has been doing this for a long time, but optical, infrared, gamma ray, this is something relatively new, and it's giving us a picture of the universe that changes on hour timescales or day timescales is something unprecedented in the history of astronomy. And there's going to be a lot of surprises, a lot of mysteries, and a lot of work to do.
When the LSST, the Large Synoptic Survey Telescope, comes online, you're going to get these observations of the night sky, the entire sky, every couple of nights, and there's going to be computers working overtime to find anything different in that whole in these images. And then astronomers are going to have to kind of go like, what's this, what's that, I don't know what this is. I think this is going to be a whole new golden age of astronomy, this time-based astronomy. And
prepare to see a lot of press releases of, here's this weird thing that we saw, we don't know what that is.
There's gonna be a lot of grants, there's gonna be a lot of 10-year applications filled with, look at all the cool stuff I found.
I don't know what any of it is.
It'll also be a great bank of targets for a future giant space telescope that may one day launch.
Some kind of James Webb-based space telescope.
Something.
2148.
What'd you say, 2148?
I said may one day launch, okay?
I'm going to take James Webb, I'm going to bronze it, and I'm going to turn it into a statue so that it can never break. It can never leave us.
If it never launches, it never fails.
It never launches, it never fails. It's there all the time. We can have it close. I think I'm just describing some kind of horror movie. All right, let's wrap things up. Kimberly, tell us something interesting that you just worked on.
So I just finished writing up about a really awesome, also transient phenomenon, a strange aurora called Steve, which you should all read about at eos.org. And for the next week or so, I'm going to be focusing on the upcoming Tess launch, which I am super excited about.
Are you going to be able to see it?
I'm going to watch it live, though I can't go down to Florida to actually see it. But I'll be watching.
Paul.
Because it's Tess.
I'll be watching.
Always watching. Paul.
So if you're a fan of statistics and pessimism, and I know you are, the past few months, I've started publishing a blog basically on my website. It's pmsutter.com/notes. And it's just once a week. It's super short. It's like 300 to 500 words on some topic on the use and abuse of statistics in science and what makes it out into the media, thoughts on the relationship between scientists and society, our ethical duty, just some of my collected thoughts that I've been having about finally actually putting them down to share as a way to start conversations and to spark debate. So feel free to go subscribe and add your comments, add your thoughts. I'd love to have a discussion around some of these issues.
Excellent.
One of my latest pieces is about how the flat Earth thing, I don't think is actually about the Earth being flat.
Whoa.
I think it's about something else.
I'll have to read and find out what it's about. What it's a boot. All right. Matthew,
Yes.
You get to have the last word here. Tell us one more time. Let's just remind everybody where they can find out, they can check out and learn about the book, and where they can, and then how they can get a free copy of the book.
Yeah, happy to. So as you see my book transiting across my screen,
I see
there it is.
There.
I get it.
You can get an advanced copy if you email me at ourcosmicstory@gmail.com. I'm happy to give it to you. We'll be running this about a week leading up to the actual launch of the book, which will be on amazon.com/author/Mathew Anderson, 1T in Matthew, if you're interested in my other works. And what I'm working on is more books.
We should make every guest give away free copies of their books to all of our listeners. That's awesome. That'd be great. All right. So let's see. So we've got a new episode. We were going to release our new episode of The Guide to Space, but Chad went on holiday. But it's super cool, all about living and working in lava tubes. So we're going to be releasing that next week. So if anyone was hoping for my new episode, I don't have one this week. It's next week. So that's what's coming up for me. An advance notice. All right. So, as always, a big thank you to all the people who are watching us live. Thanks to the WSH crew. If you want to join this community, you go to wshcrew.space. Thanks to our special guest and my co-panelists. It is always a treat to have you join us. We'll see you all next week. Bye-bye.
Bye.